So welcome to the lecture from Monday, March 11th. I'm starting out with the schedule like I usually do. You should have received an announcement from Blackboard regarding a few extra resources I put up. So specifically, I've got a YouTube video up if you're interested in using your calculator to compute binomial probabilities, and there's an associated handout as well. And as well as a video showing you how to do normal probability calculations or find normal percentiles. So this isn't required, it's just some extra stuff. If you're more comfortable using the normal probability tables, you can continue doing that. Or you could do both if you want to check yourself. So that's just completely up to you. So today we're going to finish up section 6.3, and then we're going to start into confidence intervals in chapter 7. So that's the plan. So last lecture, we had just gotten to the point of talking about the central limit theorem and talked about where it came from, and now we're going to start off with using it. So why is the central limit theorem particularly useful for us? So from here on out, we're going to be doing inference procedures, and one of the things we'll be working with quite a bit is the mean. So if you take a sample and you take the mean, we're going to want to know how well that represents our population. And we'll be doing confidence intervals, so we're going to learn about that actually today. And we'll also be doing hypothesis tests, so that'll come a little bit later down the road. And to do those, we need a distribution. So we had mentioned that if you have data that are normal, that your mean's going to be normal. But it turns out that even if you don't have normal data, as long as you have a big enough sample size, the central limit theorem says that that sample mean will have an approximate normal distribution. And so that's why the central limit theorem is so useful. We'll be able to take our means and do calculations for their probabilities using the normal distribution. So that's why that central limit theorem is an important result for us. So as an example, so if we have a sufficiently large sample size, and so the rule of thumb that I had mentioned previously was 30, so at least 30, then we're going to say the central limit theorem tells us we can use our normal distribution to answer questions about our data. And this should look like your z-score before. If you remember, previously we had an x, we subtracted off our mean, mu, from our population, and we had divided by sigma. Right, so the reason that this is different is now instead of talking about just one x, we're talking about the sample mean. So we have x bar. And so we're going to subtract off the mean for x bar, which is mu, and then we're going to divide by the standard deviation for x bar. So there's the difference. So the standard deviation for a mean is sigma over root n. Right, so you'll have to be really careful to look at, am I talking about a calculation for a single observation, or am I talking about a calculation for the mean? And if it's the mean, then you have a different denominator for your z-score. So here's you an example. So we've talked about average cost for garbage. Now we are moving on to average cost for owning a dog. So the average yearly cost per household of owning a dog is so let's say $186.80, and it has a standard deviation of $32. So there is our mu and our sigma. Okay, so now let's say we randomly sample 50 households. Okay, so there is my n, so n equals 50. So here's the question. So what is the probability that the sample mean for these 50 households is less than 175? Right, so if you want to write that as a probability statement, this is what we're interested in finding out. What is the probability that x bar, so our sample mean, is less than 175? Right, so we have our standard normal distribution to use for the calculation, which means we need to take our distribution from having a mean of 186.8 and a standard deviation of 32 to the standard normal by using our z-score. And so that's what I'm doing here. So the probability of x bar being under 175, and so I've converted this 175 to my z-score. So this is using the z for a mean. So I'm subtracting off mu, and I'm dividing by my standard deviation for the mean. So that was 186.8 on top, and 32 divided by the square root of n. So n here was 50 on the bottom. If I put this in my calculator, that comes out to be a minus 2.61. Okay, so if I can directly look this up on my table. So the probability of having a z underneath, so that would be to the left, of a minus 2.61 is 0.0045. Okay, so that says the probability of a household spending less than $175 per year is 0.0045. So we've been able to use that probability table by converting it to a z-score. So let's say we want to know what is the probability that the sample mean for the 50 households is between 195 and 200. Right? So again, this is a sample mean. Right? So that is your keyword there. So if it's a sample mean, then our z-score is going to have that standard deviation of sigma over root n in the bottom. So we're interested in, so let's try to write this out yourself and then come back and check. All right, so I'm hoping you paused it and took a minute to go through these calculations yourself. I'm going to step you through what I did. So again, the keyword here was that we're doing a calculation for the sample mean. So I want to know what is the probability that x bar is between 195 and 200. And I'm going to compute that by finding the probability for a z. And below I did my calculation. So I have an x bar of 195. That's the same as having a z. And I've subtracted off mu, which was 186.8, and divided by the standard deviation, which was sigma over root 5. And to check your calculations, I've got my difference of 8.2 on the top and my standard deviation. So on the bottom, this whole calculation here comes out to be about 4.52. And so the corresponding z-score is 1.81. And you'll notice that's positive, and it should be, because we have 195 being to the right of our mean, which was 186.8. So I did the same calculation for 200. So the standard deviation stays the same, but the difference on the top changed. And so our z-score comes out to be 2.92. So calculating the probability that x bar is between here is the same as calculating the probability of z being in here. To find those, I looked up what's the probability of being under 2.92, and I subtracted from that the probability of being under 1.91. So these I pulled directly from my table, and that comes out to be 0.0333. And if you want to just double check that, so 2.92, so that is 2.901 and 2, so that was my first number. So 0.9982 is everything that is to the left, so less than 2.92. And then the other number we needed was 1.81. And so 1.80, 1.81 is right here. So there's 0.9649 to the left, or less than or under 1.81. And so these are the two values then that I'm subtracting. And then the second calculation is just a confirmation of the same procedure. The major difference being that now we have the probability between a negative value and a positive value. So just take a minute, pause and check all your calculations. And once you've got that, so a few tips when you're going through these. So first you want to decide whether your data are normal, so is X normal? If it's not, then you want to look at what your sample size is. So is it big enough, right? So is it bigger than 30? Look for whether you're computing a probability. And if you are being given an X or given a Z, that means you're looking on the outside of your table and your probability is coming from the inside. Or whether you want a percentile. So that means you're being given your probability, and so you're going to the inside of your table and then finding the corresponding value along the outside of the table. We have two formulas for our z, and so when you're looking at a calculation, you want to know, am I talking about individual level data, or am I talking about a sample mean? So if it's individual level, then your z is going to be the difference between the mean and your x divided by sigma. So that's the standard deviation for x. But if you're interested in the probability for a mean, so a sample mean, then you have to divide by the mean standard deviation. So that's going to be a sigma over root n. And again, that works as long as you either have x being normal or you have a big enough sample size. So that takes us to the end of chapter 6. All right, so we're moving into chapter 7. And chapter 7 is the first of our inference procedures. And we're going to start doing confidence intervals and specifically focusing on our mean. And so there's going to be a couple of scenarios that we look at. The first is where we have a population and we're interested in estimating what mu is. And we are going to say that we know what our standard deviation is. Okay, so that's not that great of an assumption, but it's a place that we'll start with, and then we'll figure out what to do when we don't want to make that assumption. So far what we've done is we've used a point estimate. Okay, so a point estimate is when you have a specific value that you're using to estimate a parameter. Right, so your sample mean is often used as the best estimate when you want to know what the population mean mu is. Right, so an estimator is a statistic that is used to estimate a population parameter. Right, so the sample mean would be 1. And it's a good estimate of mu often because it tends to have less variability than other possible estimators, like your sample median or your sample mode. Right, so we're going to spend a lot of time focusing on that sample mean. So good properties of an estimator, so things we tend to look for, so it should be unbiased. And what that means is that when you start looking at your sample distribution, and you take the mean over all possible estimates that you can get, then it's actually going to come back to what you're estimating. Right? So if I look at x bar, then my expectation over all possible samples is actually going to be mu. Right? So we're estimating the right thing. Another thing that we like is we like it to be consistent. So that means that as our sample size gets bigger and bigger, then our estimator is going to give us an estimate that's getting closer and closer to the parameter we're estimating. Right? So we're going to be less likely to be far off as our sample size gets bigger. We also like them to be efficient, and what this means is that the variance is going to be small compared to other possibilities. Right? So I might have an estimate that has the right mean, so it's unbiased, but if from sample to sample it varies widely, that's going to be a bad thing. So I want it to be efficient, which means from sample to sample, that variability is going to be small. So it might bounce around a little bit, but it's going to be really close to the actual parameter that I'm estimating. So it just gives you an idea of what we think about when we talk about estimators. So an interval estimate, so this is in contrast to a point estimate, gives you a range of values that could be used to estimate a parameter. So it says that any of the values in this particular interval might be your parameter. Okay? So it may or may not have your parameter in it. So we're going to talk about how to construct an interval that gives us confidence that we have captured our actual parameter. And we're going to use what we know about sampling distributions to do this. So a point estimate, it just gives you 1, whereas an interval estimate takes into account the variability. So how precise are you able to actually get an estimate for your parameter? And this confidence that we have in our intervals is called a confidence level. And so this is defined to be the proportion of interval estimates that actually contain our true value when we consider all possible samples that we can take of that sample size from our population. So this is kind of a tricky concept in that it's actually talking about the process, right? So it says if I took another sample and I did this again and I computed my confidence interval, it's giving me the confidence that if I do this over and over and over again, how many of those intervals are going to actually capture the true population parameter, right? So it's the confidence in my procedure. Typically, people tend to focus around 95%, so you're going to see this 5% and 95% pop up a lot. So we're going to use this confidence level to construct an interval, and it's going to be called a confidence interval. Right? So definition-wise, a confidence interval is a specific interval estimate for a parameter that we determine by using our data from our sample, and then that specific confidence level for our estimate. So we're going to go through some examples. Right, so how do we construct a confidence interval? Right, so if we have a population that has a normal distribution, or if we have samples that have at least 30 observations, what do we know about the distribution for our sample mean? Right, so think about that for a second. So pause and think about what can you tell me? And as a hint, we have the central limit theorem. So what if I repeatedly take samples? What can you tell me about the distribution for that sample mean? Right, I'm hoping you got to the answer that it has a normal distribution. Right, so I can use that knowledge of that sampling distribution to say if I repeat this process over and over again, I can get an idea of where X bar should fall because I know that its distribution is going to be normal. Right? So that's how Chapter 6 is going to come in. We're going to use those tools in the construction of our confidence intervals. So the central limit theorem tells us that our X bar is going to be normal if we have a big enough sample. And in particular, if we use our z-score, that this is going to be what? So we've standardized it, so it's going to be a standard normal distribution. And what that tells us, so this 1.96, you've seen a couple of times. So if you calculate what's the probability of a z in between 1.96 and minus 1.96, let me put this down so I can type in there, it's going to be 0.95. So this comes directly from using your standard normal table. And what that lets us do, so we can make the statement that so the probability of this z being in between these values. Okay, so I can do a work through a little algebra, so I'm multiplying by sigma over root n all the way through. And then I went through and I reversed it by a negative, so I multiplied through, so some things flip. And then I'm going to add X bar. So I've got X bar added, and that just leaves mu in the middle. So this says that the probability that this interval, right, so the process of this capturing mu is going to be 0.95. So it's going to be that central limit theorem that lets us use our z-table to construct our confidence intervals, right? So we're going to be able to say we are 95% confident, okay, so then in that process, that our mu is going to fall within this interval. So it's going to be plus or minus this little bit of X bar. Right? So it will, if we continue this process, 95% of our intervals are going to capture mu. Right? But you have to keep in mind that a specific interval is either going to contain mu or it's not. The probability of us making an error, so this process having an error, is going to be 5%. So our confidence is 95, and our error will be 5%. The 1.96, so I just picked it because 95% is common, but we're going to want to be able to change that. So we might want 90% confidence, 99% confidence, and in that case, this 1.96 is going to be changing. So we need to be able to come up with those values. So some notation. So we're going to have a z, and on the bottom you see this alpha over 2. Right, so we're going to call that a percentile, and we're going to match it such that the area underneath it is 1 minus alpha over 2. Or if you like flipping that around, the probability of a z over it is alpha over 2. Okay? So let's see about deriving some of these other critical values that are going to come in handy, or these other z values. Right, so I'm going to do one of them for us. So let's look at the 98%. So for 98% confidence, then my alpha is actually going to be 1 minus that. Right, so 1 minus 98 is going to be 2. So I've got 2% for my alpha. And what I need to do is split that in between my two tails. So let's look at this figure here. Right, so here's my normal distribution. So 98% is going to refer to the in-between. I want to capture 98% of the area. So that's going to be my 1 minus alpha. And then alpha is my error, so it's everything outside of that. So alpha is going to be, we've got 98, then 1 minus that will give us 2%. And then what we need to do is actually split it in between the tails. So that's why I have this alpha divided by 2. So I'm going to have 98 in the middle, and then 1% in each tail. And so the z alpha over 2 corresponds to having the 0.01 above it. So alpha over 2 above, or 1 minus alpha over 2 below. And if I want to figure out then what the corresponding z value is, so the z value that has either 0.01 above or the 1 minus that, so 0.99 below, you need to go to my standard normal table. Right? And so the closest you're going to get is a 2.33, which has 0.9901 below it. Right? So that is the corresponding percentile for 98% confidence interval. So let's look at a few others. So for 95%, right, so my alpha then will be 1 minus, so that's 5. And then if I split it in by my tails, that means I'm going to have 2.5% above the percentile, or 1 minus that, or 0.975 below. So if you go to your table, I am trying to find 0.975 in here. You'll notice right here, you have a 1.9 and then 6 above. Right? So 1.96 is the value that will have 0.975 below and 0.025 above. And so I want to take a minute to have you pause and go ahead and find the other two values and then come back and check yourself. All right, so hopefully you practiced that. Your correct value should be 1.65 for your 90%. So that breaks 5% in the upper tail and 0.95 below. And then 2.58, which would break this into 0.005 above and 0.995 below. And remember, our rule for these is if you have a value that is right in between, to go up in your z-value. So that's why we have a 1.65 and a 2.58. So I went up in terms of the z-value. All right. So that will get you the values you need for your confidence intervals. The assumptions that we're going to have. Right, so if you are constructing a confidence interval for your mean, and you're assuming that sigma is known, so first we're going to assume we have a random sample. That's always going to be our assumption when we're trying to make some kind of an inference. Then we either assume that we have a sample from a normally distributed population, or we have enough of a sample. So sample size is 30 or above. And then again, our sigma is known. And if that's the case, then we can construct a confidence interval by taking our sample, mean, so x bar, and adding and subtracting this margin of error. So it's going to be taking our critical value, multiplying by the standard deviation for our mean. And so we're going to subtract that from the sample mean and get a lower bound, and we're going to add this quantity to our sample mean and get an upper bound. Okay, so that quantity that we're adding and subtracting is called your margin of error. Sometimes you'll see it called the maximum error of your estimate. And the idea is this is the value that we're saying that our means will fall within plus or minus this amount of error, right? So it's going to be a quantity that comes up actually when we compute our sample sizes as well. So this whole thing here is our margin of error. Comment on rounding rules. So if you are working from raw data, so we've talked about, you get a little extra precision, so go up in 1 decimal place. If you have just started from the mean and standard deviation, then round to the same number of decimal places as your sample mean, right? So match the precision that you started with. You're not gaining any additional precision. All right, so an example for constructing a confidence interval. So say we have a random sample of reading scores for 35 fifth graders, and that sample has a mean of 82, right? So that's the sample mean. Let's say that we're going to assume that the standard deviation for your population of scores is 15, right? So that is our sigma, because I'm assuming it's my population standard deviation. And what I want to do is find the 95% confidence interval for the mean reading score for all fifth graders, right? So I have a sample, and this is reflecting information at my population level, and I want an interval estimate to get an idea of what kind of precision I have. Right, so information I pulled out, so X bar is 82, my sample mean. I assumed I had the population standard deviation, which was 15. My sample is 35. And I said I want a 95% confidence interval. So we had looked up what our Z would be for that, which was 1.96. Right? So I didn't assume anything about normality, but I have over 30 values in my sample. So I'm okay constructing my confidence interval using the normal distribution. Okay, so let's take a look at my formula. So I have X bar, so 82, plus or minus my Z. That's times then my sigma over root n. And so I would suggest you compute this quantity separately. So the margin of error, if I multiply all of that out, comes out to be a little bit below 5. Okay. And so then you are going to take your sample mean and you're going to subtract your margin of error. So 82 minus 5, right? And we're going to round to the same precision as our sample mean. Right, so that gives us a lower bound of our interval of 77. And then I'm going to add it to my sample mean. So 82 plus that value is going to be, so rounded to the same precision, 87. Right, so that's the steps you'll go through. Interpretation, so we can say we're 95% confident that the mean reading score, okay, so we're talking about our population, for fifth graders is between 77 and 87. Right, so this gives you an idea of our precision. Right, so if we just started with our mean, so we had a mean of 82, okay, that doesn't give you any idea of how precise you are. Right, so that could have come from a sample of size 5, or it could have come from a sample of size 1,000. Right, and the larger the sample, the more confident, and the smaller that interval is going to be. So that's why confidence intervals are useful. Gives you an idea of how precise and how much information you really have from your sample. Now keep in mind the phrasing here. So I said I'm confident that it does. Right? It either does or it doesn't. Right? So that 95% refers to the process. It's not a probability, so that's why it's kind of weird. It's talking about the process of constructing this. So if I did this over and over and over again, so I kept taking samples of size 35, then 95% of the time I'm going to capture my true mean, right? So that's what the 95% refers to. All right, so here's you a practice example. So pause and go through and see if you can come up with the confidence interval for this scenario. All right, so to check yourself, what assumptions did we have to make? So we have a random sample from the same population. We have a known population standard deviation, and it was 5.6. We do not have to assume that we have a normal variable or a normal population because we have a big enough sample size. So our sample size was over 30. And calculation-wise, so your sample mean was 5.6. So that was a mean of 40 observations. Sigma was 0.8. Oh, that right there is a mistake. So this is 0.8 for our standard deviation. N was 40, and then since it's a 90% confidence interval, so we found that earlier, our value for Z would be 1.65. So when you stick all that together, then we have our sample mean plus or minus. So I've got my Z times my sigma divided by my square root of 40. And so my margin of error, the second quantity I calculated first. So that's a 0.208 something. And 5.6 minus that, and then rounding to the same precision of my mean gets me a 5.4. And then when I add that margin of error to my sample mean, I end up with a 5.8. Right, so interpretation-wise, what I can say is I am 90% confident that the mean age of a person's primary vehicle is between 5.4 and 5.8 years. Okay. So watch that 90% confident, so I'm confident in my procedure. And if someone asks you, so what's the probability that the interval contains the value? Okay, it's a kind of a trick. It either does or it doesn't. Right? So confidence refers to the process. The probability, you're not going to know it, but it's either going to be in there or not. So 0 or 1. And so it's easy to get those mixed up. Right? So the last thing we need to know is sometimes instead of having a sample and calculating our confidence interval, we're actually interested in starting out to plan how big of a sample do I need to take to get the level of precision that I'm interested in. Okay, so to get to that answer, we need to know a couple of things. So we need to know our maximum error, so the level of precision we're looking for. We need an estimate of our population standard deviation. So you're going to have some prior knowledge where you say, I know what sigma is. And then what level of confidence are you interested in? Right, so if you have those three things, you can plan what your sample size needs to be. And so here's your formula. And this comes directly from your confidence interval. Right, so if you want to challenge, see if you can take that confidence interval formula. So where does this come from? So this is directly from your formula for the confidence interval. And that might be, so for some of you guys who are interested in kind of looking through some of your algebra to connect with this, see if you can go from your confidence interval and derive this formula so that your sample size n is going to have to be, so it's a function of your z, your sigma, and then e is your maximum error of your estimate, also your margin of error, so that's what you're willing to accept. And when you are going through, so n, when you do these calculations, it doesn't come up as a whole number. So to be safe, always remember to round up. So let's look at an example. Okay, so a dean wishes to estimate the average number of hours that students spend studying homework. They have a previous study, and so they're willing to assume that sigma, so your standard deviation, is 6.2. A dean wants to be pretty confident in this average, so he is interested in having a 99% confidence level. And precision-wise, he wants to be within 1.5 hours. So give me the sample size needed to get within 1.5 hours of that mean. Right, so my E is 1.5. For 99% confidence, my alpha is going to be 0.01. and then my sigma was 6.2. So that's something that we would assume. So for z of alpha over 2, so we calculated it earlier. I give you a little extra precision here, but you could. So another approach, we had talked about rounding up, so 2.58 would be another possibility here for our z. So I actually went in between. So you might try using 2.58 and see if it makes a difference. Right, so plugging this in, so my sample size that I would need, so I put in my z times my standard deviation divided by my margin of error that I'm willing to accept. And computing this, so I've got the n side, compute that value, and then don't forget to square it. That comes up to be a little over 113, right? So rounding up, the dean is going to have to survey 114 students to have that level of confidence and to get an interval that is within 1.5 hours, right? So this is useful for your study planning. So give this one a try. So pause the video and come back and then check your answers. All right, so reading through this, you should have gotten that the maximum error they were interested in is 2 feet. Your confidence is 98, so your alpha is going to be 1 minus that, so 0.02. Standard deviations was assumed to be 4.38. And the critical value, or the z, that corresponds to that 98%, we found earlier, and it's 2.33. So when you went through your calculations, you should have come up with a value a little over 26. And so to reach these goals, the scientists would need, so round up, 27 measurements to achieve those goals. All right, so that's a sample size calculation example. To remember, so just remember again, so confidence level, so it's not a probability, it's not the probability that our interval contains our parameter, either does or doesn't. Again, it's our proportion, right? So if we constructed 100 confidence intervals from random samples using a confidence level of 95%, then about 95% of those are going to contain our parameter. So if you think about it, so why do we say about? Again, this is a random process. So we say about because if we're taking samples, if I take 100 samples, there's randomness in that. And so the process tells me that around 95. If I keep doing it, so if I take 1,000, then I'm going to get closer and around 95% of those 1,000, right? So it won't be exactly 95%, but it will be close. And so as an example, so if I say I have a mean for a certain population and it's 15, and I took 50 samples, right? So imagine doing that randomly, right? So each person in our class, and then we recruited some other people, and they went out and they took samples, right? And each person constructed their own confidence interval, right? So how many of those intervals should contain the value for the mean? So if I look at all of those different intervals, then 50 times 0.95, right? So that's what? You want to use your calculator. So 50 times 0.95, so 47.5 or somewhere, so between 47 and 48 of those intervals should contain 15. And what does that mean about how many should not? Right, so that means that 2 to 3 of the intervals will not contain the actual mean. So it's this process that we're talking about. So if I do that, so this is an example of going through and actually taking 50 samples. Right, so I've got my mean here, and so I've gone in and I've actually sampled and constructed a confidence interval, so 50 times. And so in this particular experiment, it came out that 3 of them missed, right? So here is an interval, and you'll see that it contains 15. But this one in red missed it, right? So it overshot it, These two missed it by a little bit, and they missed it and they're a little bit below. All right, so that process, so 5% of the time you're going to be unlucky when you take that sample and you're going to miss your mu, right? But otherwise it either is or it isn't, and 95% of the time those intervals actually captured that true mean. All right, that takes us into the end of 7.1. And I think I'm going to stop there. So we will pick up with 7.3 when we finish with our exam. So it'll be a week from Monday, so March 18th.